Hi, welcome back. So we are in Chapter 5, Prediction by Probability at the outline of Univariate concept of probability at the section of probability of a discrete value. We have explored so far a number of special distribution when the variable is discrete. Now, what we're going to talk about actually is a different kind of distribution we call cumulative distribution function, as known as the CDF of a random variable, is another method to describe distribution of a random variable. And the advantage is that this kind of distribution is applicable for any kind of a random variable. So regardless, could be a discrete or a continuous. Let me give you an example. We toss a coin, for example, say number of trials twice. We are asked to define x to be the number of heads that we observe. First of all, let's define the range actually. 0, maybe 1 head or 2 head maximum. We're asked to find the CDF. The cumulative distribution function of f of x is equal to the following situation. 0 for any x should be less than 0. So we could see from the very beginning there is nothing in the range that indicate that I could have a value of x less than 0. We've got 1 for x to be between the following value. It's larger than equal to 0 but less than 1. Well, that include this but doesn't include this. And then we've got larger than equal 1 but less than 2 will be this one and this one. So you are accumulating everything before that is going to be a 3/4. Lastly, x to be larger than or equal to 2. In this case, we're going to sum up 1/4 plus 1/2 plus 1/4. That will be 1. If I want to plug that, cumulative distribution function can be useful in many applications anyway. Perhaps in some other following example, we can encounter one of them. Just I wanted to leave that with you so you could be familiar with the subject. Next, we're going to be looking at something called the expectation and variance. Well, what is expectation in general denoted as E of x, where x is actually a discrete kind of variable. As the following, we say this is going to be the sum x sub q k here, xk must be in the range of x multiplied by its probability x sub k. This is the basic idea behind the expected value. So if you would like to capture the expected value for any discrete value, the idea is take the value that you want to expect within the range of x and multiply by its probability. Well, this probability can be any of the probability we discussed previously. It could be binomial, could be polynomial, could be geometric, could be Poisson, any kind of distribution. So the idea is maybe if you understand the concept of expected value, the things will become a bit easier. I would like just to show you a few examples on how to derive some of these expected value. Let's start with the simplest one by a polynomial. The range here only 0 or 1. That's all. I mean, no more than that. Probability of x is equal 1 equal p. Probability of x is equal 0 is equal 1 minus p. Expected value of x, given that it is a polynomial distribution, is as simple as saying 0 multiplied by its probability, which is 1 minus p, plus the second range, which is 1, multiplied by p. Now, all of which will lead you to just the probability itself. Let's see the expected value of x given that is distributed by a geometric. We know the range of x in this case, and we know the probability, the expected value of x. It is the sum. We have k, any of these value 1 or 2, multiplied by this value here. We already know the geometric sum formula. If you remember, I think we discussed about that sometimes before. Luckily, we can actually convert this geometric sum to the form that we want to take the derivative with respect to that. Final expected value will be 1 over p. Let's try to find x as it is distributed by Poisson distribution. Given lambda, I don't really have to derive this. The expected value of x just equal to the lambda. Now, how to prove that? Using the logic by taking only the range, and we know the probability mass function. If you do this and mathematically derive, you reach out to the fact that actually the expected value is just equal to lambda itself. So we could check the last one, the binomial. Well, binomial, it is a number of n of polynomial. It is equal just np. Maybe one more important thing that we can discuss about concerning the idea of variance as well. Let's consider a case like you have two random variables. Let's say the probability of x, and let's see the probability of y. I want you to tell me what is the expected value of x here. Well, the expected value of x, 0.5 multiplied by expected value of 100 plus 0.5 multiplied by the 100, sum up to 0. This is the expected value of x. What's the expected value of y? It's equal to 0. So both expected value had the same exact mean value, which is 0. And now their distribution is completely different. If you look at the distribution of x, it's a wide range, but the distribution of y is constant at that 0. What is happening? The problem is that the variance is measure of how spread out the distribution of random variables. So their distribution here cannot be captured by speaking about the expected value. That variation will be captured using the variance formula. And the variance, basically, it says to be actually of x is nothing but the expected value of x minus what's so-called ux square. And if you do the calculation, that will give you 10,000. Value of y here, which is equal to 0 as expected, actually. So you can see, as we expect, x has a very large variance, while the variance of y is 0. Note that the variance of x has different unit than x. For example, if x, say, measured by meters, then the variance of x is in a meter square. And to solve this issue, we tend to use something called the standard deviation. Sigma of x is called, which is equal square root of the variance. So if I want to capture the standard deviation here, which is going to be 100, is going to be square root of 0. Again, it is 0. That was actually the end of this section, where we have discussed most of the distributions and the idea concerning the expectation, the variance, the cumulative distributive function. Given variable happens to be a discrete type of variable. Now we are actually ready to move on to discuss the second kind of variables if it happens to be continuous. That's exactly what we're going to do next. I will see you then.